Okay, hello, welcome. We are continuing with chapter 8, and we're now going to be doing section 2, which is testing the difference between means. But now uh, we will assume that sigma 1 and sigma 2 are unknown. Okay, so we've got one objective, which is learning how to perform a t-test for the difference between two means with independent samples with sigma 1 and sigma 2 unknown. So our syntax for this section, the syntax is going to be two sample t-test. Okay. And instead of having sigma 1 and sigma 2, we will have S1 and S2, which are the sample standard deviations. All right, let's go. Here we have the requirements listed. This is very similar to the two sample z-test for the difference between means. I'll just draw your attention to this difference here, which is that sigma 1 and sigma 2 are unknown. Okay, everything else is the same. Our standardized test statistic. We still have the same test statistic. So this is our test statistic. This is our test statistic. Is x1 bar minus x2 bar is our test statistic. The standardized test statistic, of course, is taking the z-score of the test statistic. And now we'll have something actually that is a little different. When we go to compute our standard error, our standard deviation, sometimes also called the standard error because we are dealing with the sampling distribution, the standard error or the standard deviation depends on whether or not the population variances are equal. So remember, variance is just your standard deviation squared. So your population variance is going to be sigma 1 squared and sigma 2 squared. Those are your population variances. So these are the two cases we have. So the first case we have is what if your variances are equal? And the second case we have is what if your variances are not equal? Now, I want to point out that the definition of equal changes depending on the context. So for some, there is the following rule of thumb. What is this rule of thumb? Regard variances as equal if they're pretty close to each other, right? Which is to say that regard them as equal unless one of them is more than twice the other. Okay, so variances are equal unless one sample variance is more than twice the other sample variance. But, and actually this isn't even sample, I think this is population, so I've got a typo here. So it should be one population variance. So the reason I wanted to point this out, right, this rule of thumb, is because it is something that is out there. So you have to be careful when you're reading, say for instance, when you transfer and you're, in undergrad or grad school later on, when you're reading, say a survey or you're reading results or an article or research, make sure that you are aware of their definition of equal, right? So when they say equal, do they mean exactly the same variance, or do they mean the variances are kind of close to each other? Okay. For our textbook, and for the final exam, we mean equal means exactly the same, right? So equal means exactly the same. So we're not really approximating and saying, oh, they're almost the same. No, we're going to mean that if they're equal, that means they are the same number. Your variances are the same. And if they're not equal, your variances are different. Okay, so we've got this kind of complicated. So let me clear my screen a little bit. we've got something that is kind of complicated in terms of our formula here. So the formula for the standard error, which remember is the denominator of your standardized test statistic, the formula is this factor right here, which is sigma hat, times this factor right here, which is the square root of 1 over n1 plus 1 over n2. And the formula for sigma hat is up here. So I'm just going to calculate this and show you how to calculate it for one example, just so you can be aware and be exposed to it. But, you know, in general, you won't need to calculate your sigma hat because your standardized test statistic is going to automatically calculate it. Okay, also, let's take note that we've got a different definition. Here, the degrees of freedom matter because we're going to be working with t-test, right? So with a t-test, you've got a t-distribution, which means there's several different t-distributions, and which t-distribution you have depends on your degrees of freedom. For a z-distribution, the standard normal distribution, there's only one standard normal distribution. It has a center of 0 and the standard deviation of 1. But for a t-distribution, there are infinitely many, right? And it depends on your degrees of freedom. And the larger your degrees of freedom, the closer the t-distribution approximates the standard, or the standard normal distribution. Okay. Here, the formula for your standard error, if your variances are not equal, is the same as the formula for standard error for a z-test. And just take note that the degrees of freedom is just going to be the smaller of n1 minus 1 and n2 minus 1. Okay, so we'll see how to apply these. Now this chart is a nice chart, and it kind of highlights the question of, do you use a normal distribution or do you use a t-distribution, right? And you can pause and look at it. Okay, so I just wanted to point out that this chart is assuming that your samples are independent. So remember, if your samples are dependent, then that's section 8.3, and we have a different approach. Okay, so that's asking a hypothesis test with two samples for the difference between means, with independent samples, and with sigma 1 and sigma 2 unknown. Okay, so here's our setup. So let's verify that we've got a random sample, and let's verify all that stuff. Okay, here we go. Our samples are random samples. Verify that sigma 1 and sigma 2 are not known. They're not. In fact, all we've been given is S1 and S2, right? The sample standard deviations. We are doing a test for the mean, the difference between means, the difference of means, because look here, look at this sentence. It says, can you conclude that there is a difference in the mean, right? So difference in the means, it's written out explicitly. Assume the populations are normally distributed. That's important because look at our sample size. Our sample sizes aren't large enough for us to conduct the test unless we know the populations are normally distributed. And then the last thing that we'll need to know just for our computation's sake is that the variances are not equal. Okay, so first thing we want to do is determine our null and alternative hypotheses. So we need our claim. So what is the claim? The claim is, let's go back. Can you conclude that there's a difference in the mean mathematics test scores for the students of the two teachers? Okay, so the claim is that there is a difference in the test scores, is a difference in the test scores of the two teachers. Okay, now we're going to translate that into a mathematical statement, and we'll just say mu1 isn't mu2. And now here mu1 is the mean test scores of first teacher, and mu2 is the mean test scores of the second teacher. So pretty straightforward. So we've got our claim. We write the complement, which is going to be mu is equal to mu2. Mu1 is equal to mu2. And the last thing we do is we figure out which statement is our null and which is our alternative hypothesis. All right. So this is our setup. And now the next thing we need to do is we need to figure out our test statistic. So our test statistic, because we're doing a difference hypothesis test for the difference of means, our test statistic is going to be x1 bar minus x2 bar, which in this case is 473 minus 459. 473 minus 459. So note that there's actually a typo here because these shouldn't be dollar signs. So we can erase those, right? There shouldn't be dollar signs because they're test scores. Okay, and so now 473 minus 459, that is equal to 14. So put a little red box for our test statistic. Now that we've got our test statistic, let's compute the standardized test statistic. So for the standardized test statistic, we will need the following formula. T equals x1 bar minus x2 bar minus mu1 minus mu2. And all of that is divided by the standard error, which is going to be the sample standard error. The standard error. This is not actually the sample standard error. This is the standard error for the sampling distribution of the difference in sample means. Okay. So that's a really long and complicated way to explain it. Now, the thing to note is that since the population variances are not equal, because we were told that in the problem, so population variances are not equal, we're going to have to use a different formula. So that we need to know that in order to determine which formula we're going to use. So again, remember, we're solving this problem using rejection regions. Okay, so let's look at our flowchart. Are both population standard deviations known? No, they're not known, right? We only have S1 and S2. We don't have sigma 1 and sigma 2. Okay, are both populations normal? Yes. Okay, are the population variances equal? No, they're not equal. So then we need to use the t-test with, and now here's our formula for our standard error. Okay, and then also this is going to be our formula for the degrees of freedom. Okay, so for our standard error, since our population variances are not equal, we'll use S, x1 bar minus x2 bar is equal to S1 squared over N1 plus S2 squared over N2 square root. So now we can plug this in. So S1 is 39.7, S2 is 24.5, N1 is 8, N2 is 18. Okay. So 39.7 squared divided by 8 is going to be 197.011. 24.5 squared divided by 18 is going to be 33.347. So we add those up and take the square root, and we get the square root of 230.358, which is about 15.178. All right. So this is our standardized test statistic. Now remember, we're going to need the standardized test statistic in order to do our test by the rejection region, because we're going to see, is the standardized test statistic in the rejection region? Okay, so now the next step is for us to figure out our rejection region. So our rejection regions is going to be determined by two things. One is alpha, and the other is the critical values, the critical points. So we know we have a t-distribution. So this is a t-distribution. And in order to know what our t-distribution is, we need to know what are the degrees of freedom. So the formula from before said, or the chart reminded us that we need to take as our degrees of freedom down here. Let's see here. Degrees of freedom is equal to the smaller of N1 minus 1 and N2 minus 1. So for us, N1 is 8 and N2, remember, was 18. Okay, so then we would have 7 versus 17. So we're going to go with the smaller of them, which is 7. So our degrees of freedom are actually going to be 7. We've got 7 degrees of freedom. And we're going to need to know that information for when we calculate our critical values. So our degrees of freedom is going to equal 7. Okay. The alpha is 10%. So it's right here. Alpha equals 0.1. Okay. So alpha is equal to 0.1. And the last thing we need to know is what type of hypothesis test is this? Is it left-tailed, right-tailed, or two-tailed? So we go back to our alternative hypothesis, and since it is mu1 is not equal to mu2, we are going to have a two-tailed test. So we've got two tails, and the area is 0.1, so the area in each tail needs to be 0.05, or half of 0.1. Okay, and our critical values are going to be whatever value is kind of the border for those tails. So to find our critical values, we can use inverse t. And we need to put in the area, which is 0.05, and we need to put in the degrees of freedom, which is 7. And that's going to give us, what number will that give us? That will give us negative 1.895. So we can go ahead and label our little graph here, negative 1.875. And the other critical value is 1.875. Okay, and of course the center is, the mean is 0, because for t-distribution that is the mean. And our rejection region is anything more extreme than negative 1.85 and positive 1.85. So anything back here or anything above here. So rejection region is going to be from negative infinity to negative 1.875 or 1.875 to infinity. Okay, so here we're using interval notation. Now, our standardized test statistic is 15. Our standardized test statistic is 15.178. That is a pretty, no, this is not our standardized test statistic. So the reason why I was kind of surprised is because 15.178, if I go to put this on my graph, it's going to be like way over here somewhere, 15.178. And that's really, really, really large. So I went back and I said, hey, that's our standardized test statistic. And in fact, no, it's not. That is the standard error. So to get our standardized test statistic, we need to remember that for our hypothesized difference of the means, we use 0. And for our test statistic, we already calculated that. That'll be 14. So our standardized test statistic, t, is going to equal 14 minus 0 divided by 15.178, which is equal to about 0.9224. And now that is a much reasonable value to put on here. So if we've got 0.9224, that's going to be about halfway, 0.9224. Okay, and it is not in our rejection region. So test statistic, our standardized test statistic, is not in the rejection region. So we will fail to reject H naught. And since our claim was HA, if we fail to reject H naught, that means there's not enough evidence to support the claim. Insufficient evidence to support the claim. And this is at the, what is alpha? Alpha was 10% at the 10% level. 10% significance level. All right. Okay, so we won't need this. We won't need this form. It's got the same information here, and the picture is a bit better than my picture down here for the rejection region. And so now let's look at example 2. So take a moment to read it over. Okay, so let's go ahead and figure out what we are conducting. Are we conducting 2 samples for the difference between means, independent samples, sigma 1 and sigma 2 unknown? Let's look and see. So we definitely can see that this is a claim. The claim is that the calling range is greater than that of its leading competitor. Now, we would have to know that calling range is something that's measured in feet, and so you would take an average of calling ranges, or the average of ranges, in order to get your ultimate calling range, right? So if you have a product and you say it's 2.4 gigahertz, it's the range. No, 2.4 gigahertz wouldn't be the range. The range would be, I don't know, something. They're saying it's about, perhaps the mean is somewhere around 1,200 feet. I don't know. But so you have your 2.4 gigahertz cordless telephone, and you make a statement about its range, and you have to print this on the box, right, or the package that you're selling it. And what you're giving is just an average. It's a mean range of all of the cell phones that are produced, or the cordless telephones that are produced. Okay. So even though the problem doesn't directly say find the difference, or the claims that the difference between means is negative, right? Even though it doesn't say that, by reading it, you can interpret that we are, in fact, doing 2 samples for the difference between means. And let's check about our samples. Are our samples independent? Okay, you perform a study using 14 randomly selected phones from the manufacturer and 14 randomly selected similar phones from its competitor. Okay, so what we need to know here is, or the assumption is, that our samples are going to be independent because the competitor and the manufacturer, they're not creating the same phone. Okay, so that will be our assumption, is that our samples are independent. And of course, the last thing is that sigma 1 and sigma 2 are unknown, which we can get from the fact that we're given S1 and S2, and there's no mention of population of the first population standard deviation or the second population standard deviation. Okay, so we know which test we're doing. We're conducting a hypothesis test for the population, with a hypothesis test with 2 samples for the difference between means, with independent samples, and sigma 1 and sigma 2 unknown. Now the requirements for the test are going to be that sigma 1 and sigma 2 are unknown, that we have random samples, that we have independent samples, that our populations are normally distributed, or our sample sizes are at least 30. All right. So to determine the null and alternative hypotheses, what we're going to do is go back to the statement of the problem. And the claim is that the calling range is that the manufacturer's calling range is greater than the competition's calling range. Okay, so let's go ahead and turn this into our null and alternative hypotheses.
It's 10:15.
So the claim is that the manufacturer's range is greater than the competition's range. Okay, now how do we translate this into a mathematical statement? Well, first I'm actually going to put in here mean, right? Competition's mean range, because remember we just talked about how in order to determine the range for a product, you're actually taking the average. Okay, so to translate this into a mathematical statement, we'll have mu1 is greater than mu2, and now mu1 is going to be the mean range of manufacturer, and mu2 is going to be the mean range of the competition's phone. Okay, now we've got our statement, mu1 is greater than mu2, so we do the complement. The complement is going to be mu1 is less than or equal to mu2. Our null hypothesis is the complement, and our claim is the alternative hypothesis. So let's go ahead and put that in. Our null hypothesis is mu1 is less than or equal to mu2. Our alternative hypothesis is that mu1 is greater than mu2, and the claim is the alternative hypothesis. The distribution that we're going to use is the t-distribution because we don't know the population standard deviations. The test statistic is going to be x1 bar minus x2 bar, which is going to be 1275 feet minus 1250. So let's just check that. Right, so the sample of the manufacturer's phones had a higher range than the competition's, right? But we're going to test to see if that is significant enough to, for the manufacturer to claim that their range overall is higher. So we get our test statistic is 25. What is the standardized test statistic? Okay, so for the standardized test statistic, it will be it'll be t equals 1.811. And again, this will be, you can get this from your printout, the output from your TI-84 from your calculator will give you that. The p-value is going to be 0.0404. Now for the p-value, pretty much the only information that you'll need to add that isn't explicitly stated is that choice of greater than, okay, so that you know what type of hypothesis, so that the calculator knows what type of hypothesis test to perform. So you'll need that information, and you'll also need the information of x1, s1, n1, x2, s2, and n2. Okay, the last bit of information that you'll need is assume the populations are normally distributed and the population variances are equal. So you are assuming that the variances are equal. So let's see here. Okay. So on the TI-83 and the TI-84, you'll also have when you do a two-sample t-test, you will be asked a question about if you want to do pooled or unpooled. Okay. So I'm not sure if I highlighted this, but you'll be doing a pooled, you'll choose pooled if your variances are equal. And you'll choose unpooled if your variances are not equal. And essentially, the deal with pooled and unpooled is you've got two samples or two populations really. And if the populations have similar variance, then you can just kind of group them all together and treat it as one big population. So you can pool the populations, pool the data. If the variances are different from each other, then you would want to keep track of those differences and you wouldn't want to combine the distributions. So that's what's kind of behind that pooled versus unpooled, okay? And that's also why there's a rule of thumb, or there's some leniency, right? So you could say, hey, these variances, the variances between these two populations they're not exactly equal, but they're close enough. We can work with it, right? And then you might say, well, if one of them is more than twice the other, then, we really have to use a different method. So that's the motivation behind having a rule of thumb, and that's the motivation behind having two options, pooled versus unpooled, when you're doing your calculations. So here, remember, unpooled is if your variances are different. So here we are assuming that this is our problem. We're assuming that our population variances are equal, so you will be using pooled. So on your calculator, for your calculator, you're going to be doing the two-sample t-test, and you will need to enter in the options of x1 bar, x2 bar, n1, n2, s1, S2. You'll need to tell it that you're doing a right-tailed test. So you'll need mu1 not equal to mu2 greater than mu2 or less than mu2. And you want to choose the option that's greater than mu2. And the last thing you'll need to do for pooled versus unpooled, you'll need to choose, in this case, pooled, because your variances are equal to each other. Okay, so when you do that, you'll get this output here, your p-value, your your generalized or your standardized test statistic, and in one or two complete sentences explain what the p-value means. It means the probability of obtaining a difference between two samples or between two sample mean phone ranges, which is as extreme or more extreme than 25 feet. And this is all assuming, because what are we assuming? We're assuming that the manufacturer's range is less than or equal to the competitor's range. Manufacturer's range is less than the competitor's range. So assuming that let's see, what do we have here? Assuming that the manufacturer's range is less than the competitor's range, what's the probability of obtaining a difference between the two sample mean phone ranges, which is as extreme or more extreme than 25 feet? That probability is 0.0404, which is approximately 4%, right? And so we can kind of look here, what is our alpha? We can go ahead and make a decision. Alpha is 5%. So alpha is 5%. Same thing as 0.05. So our decision is going to be to reject H naught. So the idea is that it's very unlikely, there's a 4% probability that you would end up with the manufacturer's phone range, sample phone range, 25 feet more than the competition's phone range, if really the manufacturer's overall range is less than the competition's overall range. So we're going to reject H naught since P is less than alpha, okay, or P is less than or equal to alpha. We're going to reject H naught. And the interpretation of the decision, well, so now we rejected H naught and the claim is HA. So at the 5% significance level, there is enough evidence to support the claim. Support the claim, the manufacturer's claim, that their phones have a larger range. Okay, and I think the last thing, I don't know why I always wait for the end to do this, but the last thing we want to do is sketch our sampling distribution. So because we're doing a t-distribution, let's label the axis as t. Our p-value is going to be 0.0404. Okay, so now 0.0404. All right, so 0.04, we're going to put that is our standardized test statistic is 1.811. So if this is 0, We're going to estimate 1.811 is about here, so it's really, really small, and that area is equal to 0.0404, right? The area going on forever. And we are done. Okay, so we've got the nitty-gritty details there. Thank you.